function am I showing you here? What kind of an equation? Of quadratic. It's a quadratic function. How many solutions are there? How do you know? What's that? Yeah, but that's not how we know that that's how many solutions there are. And again, how it's not a maximum of 2, it is 2. How do you know? That's all of those are correct answers. But for every polynomial, you can look at it instantly and tell how many solutions there are. It's because of the square. Whatever your highest power is on the variable, that tells you how many solutions there are. And that means there are 2 solutions. Not 1, not none, not at most 2, exactly 2. Completing the square, awesome, but kind of a pain when A is not a 1, and a bigger pain when B is not even. So somebody said, I'm tired of this. I can't do this all the time. I need a better way when it's not easy because I got my t-shirt on. These t-shirts have been around for years. Long before there were t-shirts, these t-shirts were around. What was wrong with this guy? He was lazy. He's looking for an easy way out. So what did he decide to do? He said, look, I'm going to do a little work here, and I'm just going to do this problem right here and solve it for x by completing the square. Okay? So here's the process. If we complete the square according to the steps, we would put c on the other side, and what would I do next? Not take out the b, not take half of b. Get rid of a. Very good. We have to make sure that this is a 1, and I don't know that it is right now. It's a. So I have to divide everybody by a. So x squared plus b over ax equals negative c over a. You can see that this is really getting ugly. But again, this guy is hoping that this is going to make life easier. We're going to complete the square. Plus blank, plus blank. And over here in the circle, what am I going to put? Half of, so half of, which is b over 2a. Okay? Take half of b, and b in this case happens to be b over a, gives you b over 2a. When you square this, and this is positive, when you square this, on the top you get squared. On the bottom you get 4a squared. So we have b squared over 4a squared. It goes in the blanks. Now this is a perfect example of why you look at this and you go, I don't even understand how to factor that left-hand side. But the left-hand side right now is what? What is this thing?
B over 2a.
It's a perfect square trinomial. How do you know it's a perfect square trinomial? We made it perfect square. So every single time you get to this stage, it will always factor. How? How will it factor? Not plus or minus. So in general, it will always be the variable, the number in the circle, wrap it and square it. And this is a positive b over 2a, so this has to be x plus b over 2a. On the right-hand side, we have a problem. We can't really combine these unless we get common denominators. What's the common denominator going to be?
4a. Or not. 4a squared.
4a squared. So this is going to stay 4a squared, and this will be b squared. We're going to have to multiply this by 4a, so this is going to be negative 4ac. When we combine those, since this is negative, we're going to put it second. and I'm going to get x plus b over 2a squared equals b squared minus 4ac over 4a squared. So just like we've been doing all along, we're now solving for x. This is squared. So in order to get rid of squaring, we square root. X plus b over 2a is going to equal plus or minus the square root of the right-hand side. We don't need to multiply the bottom. Oh, absolutely, simplify the bottom. So we root top and bottom. And what is the square root of 4a squared? 2a. We already have the plus or minus in front of it all. How do I solve for x?
Subtract 2b over a.
No.
B over 2a.
So we're going to get x equals negative b over 2a plus or minus square root of b squared minus 4ac over 2a. And they already had a common denominator, so we combine them. So in effect, what this person did, he said, look, if this is what x is equal to from standard form, if you know a, b, and c of any quadratic equation, we can plug it into this, and we'll be able to solve for x instantly. Well, it's not as instant as factoring, but it's pretty instant. And it takes you right to the solutions. So when you're not factorable, another method that you can use is called the quadratic formula. And most of you have seen this. Okay, and I know some of you started sniffing it out somewhere along the way here, and you start to realize, oh, I've seen these things before. And in Algebra 1, how did you learn the quadratic formula? They went, here you go. Why does it work? I don't know. Here, just do it. This is where it comes from. You guys need to be able to understand that this quadratic formula comes from completing the square. And it's completing the square in a generic form of the standard form. And there's no reason for you to just take this without explanation. In Algebra 1, most of what we do, we just say, here, do it. This is, you don't need to know why. Okay? It's the same thing your parents do. The younger you are, the more you do it because I said so. As you get older, you need to be given explanation. You need to understand where this comes from. Now, there's a couple things we're going to talk about today that I don't think are overly valuable. Okay? I don't think they're overly valuable. It's one of those things where, okay, it's interesting, but really it's not what I want to know. Okay? If you told me when I was in college, you say, I know who you're going to marry. Really? Yeah. If we have that conversation, and then you tell me she's one of the women on the planet. Okay, you haven't done me any favors. The same thing is going to be true about this thing in here. This thing under the radical is called the discriminant. This discriminant can tell you about the roots, about the solutions. It can give you some description about them, but it's not going to tell you who they are. This discriminant is a determining factor. And what's under the radical, let me go to that just for a second. The b squared minus 4ac, if it's positive, squared minus 4ac is positive, you're going to have two real solutions. It means the graph will cross the axis twice if b squared minus 4ac is a positive number. If b squared minus 4ac is equal to 0 exactly, you're going to be touching the x-axis at the vertex. And there's only one real solution. That solution is called a double root. And on top of that, it means your original quadratic right here is a perfect square trinomial. And then the third possible situation you could have is that the b squared minus 4ac, the discriminant, is negative, which means you have two imaginary solutions, which means the graph is either a horseshoe up above the x-axis or horseshoe down below the x-axis, and there's, bless you, no x-intercepts that you can see visually. They're imaginary. We're back to, you know who my wife is, and you're telling me she's one of the women on the planet. Okay, you really haven't done much for me except you've eliminated the fact that I'm not marrying a guy, which, okay, that's fine, but I knew that. This isn't telling you much. It's called the nature of the roots, and to be totally honest with you, I just don't care. Now, that may be the wrong statement for me to be making standing up here, but honestly, I don't care what they're like. What do I care about? Meaning, who they are. These, tell me, who are they? What are they? What are these x values? Tell me who this is. And then, if they're real, obviously, they're real. If there's only one of them, there's only one of them. And if there's none of them, there's none of them. They're imaginary. But I want to know who they are, not what they're like. She has a great personality. Okay? I don't want to know what they're like. I want to know who they are. So we're going to look at this. We're going to go through some examples here with quadratic formula. And by the end of today, I want you to be able to tell me when you should be using quadratic formula, when you should be using completing the square, and when you should be using factoring. Okay? And that's what you want to get out of what we're doing right now. So what is the first mandate before you can use the quadratic formula? If you're not in standard form, you're not going to get the solutions. So you need to be in standard form, set equal to 0 or set equal to y or f of x, but it's got to be standard form. The minimum that I expect from you, which will get you virtually all credit on a problem like this, is to show me the plugin. The plugin looks like this. If that's on your paper and you make a mistake after that, you'll lose a point. No big deal. Of the people who make mistakes after this, very few of them have this on their paper. Let me say that again. People who get this problem wrong, the vast majority of them never wrote this down. You know why? Because they think they can do it in their head. And you can. There's a lot of things you can do in your head. But I will give you virtually all the credit on the test questions. They're worth like 3 or 4 points on the test. If this is there and then you make a mistake below that, I'm good. And again, you have a calculator that can do a lot of the work for you, but again, we want exact values, so I don't use the calculator too much. I try to go through and do the work on hand. That's a personal choice. You guys have calculators. Use them, don't use them. The more you can do without a calculator, the better math student you will be. That is an absolute 100% fact. If you want to be a better math student, stop using your calculator. So 5 plus or minus the square root of 53 over 2 nicely through that. Most of you have seen quadratic formula before. So let's have you try this one right here. X squared plus 10 is equal to 6x. Okay, so a lot of good. I saw a lot of people doing the right thing, starting off with standard form, and then you need to show a straight plug-in. That's the opposite, parentheses, negative 6, plus or minus, radical, parentheses, negative 6 squared, minus 4 times 1 times 10. This fraction has to go all the way across. It's not just under the radical, it's the whole thing over 2 times a. Bless you. So now it's about simplifying. X equals 6 plus or minus 36 minus 40 over 2. And I saw a lot of people who had stuff that looked like that. And then x equals 6 plus or minus square root of negative 4 over 2. And then I saw people deviating from what they showed from here. Trying to skip steps. That's not doing you any good to do that. The square root of negative 4 is 2i over 2. So what you're looking for is all three of these divisible by the same thing. And in this case, yeah. So they all are divisible by 2. So you're going to end up with x equals 3 plus or minus I. What does that tell you about this parabola?
It's imaginary.
It's not. It has no real solutions. So what does it tell you about the graph of this parabola? Right? So what does it tell you about the graph? It has no x-intercepts. Tell me more. Never touches the x-axis, right? Tell me more. Who cares? Like, true, but I didn't mean it like that. That's not what I meant. I just don't care. Tell me about the graph. That's the important thing. And you should know this right now. You should understand what this means in terms of the function. If I looked at the function where y is equal to x squared minus 6x plus 10, you need to understand what this means graphically. What can you tell me about this graph? It is a parabola. What else can you tell me? Why do you think that? Who's it? Who's the y? Okay, and that's what I wanted to get at. You were looking at way down here. Just look at this equation. What tells you whether it opens up or down? What's the determinant? Not B. It's A. What is A called? What do we call A? We've been doing this for weeks. What's it called? Attaboy. Vertical stretch factor. A, in this case, is a 1, right? Positive. What does that tell you about a parabola? Horseshoe up. It's got to be a horseshoe up. Does that make sense to you? So that's what I was looking for. It's horseshoe up. Now, if you combine that with everything else we know, where's the vertex? Not specifically, in general, above the x-axis. All we know from 2 imaginary roots horseshoe up is the graph has to be something like that. Now, it might be over here. I don't care, but it's not going to have a vertex below. Everybody see that? Try this one. All right, so let me catch up to some of you guys. 16x squared. When you subtract 17, you should get minus 40x. and then plus 25 is equal to 0. Everybody get that? Minus 40 and a plus 25. Okay? If we're directed to, which we are, I'm directing you to solve this by quadratic formula, then x is going to equal the opposite of negative 40 plus or minus the square root of negative 40 squared minus 4 times 4 times, what was the third one? Thank you, 16 times 25. All over 2 times 60. Did I make a mistake? So positive 40 plus or minus the square root of 1600 minus 1600 over 32. 40 plus or minus the square root of 0, if you need to write that down, I guess that's okay. That's going to be 40 over 32. And if you reduce that, that's 5 over 4. So if we're solving, the only answer we're going to get is 5 over 4. Yes, no? Did you find it though? Oh, so you had a 17 here. Okay. Everybody else good? Again, if you check this in the discriminant, it becomes a 0, then we know that this parabola has a vertex that is on the x-axis. And the x-coordinate of that vertex is 5 over 4. And that this graph is going, according to this equation, it would be a horseshoe up with a vertex at 1 1/4, comma something. Yeah, this is a PST, right? So once you get here, the square root of 16 is 4, the square root of 25 is 5, 4 times 5 is 20, and that's half of 40. It wouldn't have saved you with that 17, but that's the idea. And we definitely want to factor it if it's factorable. Okay? And this one would have been factorable. Okay? If you want to learn about the discriminant, these notes are online. You can memorize that, but again, I don't care very much about, ooh, tell me about the roots. I want to know who they are. And let's get right down to it. We really want to know what the name of the roots are. Even if they're imaginary, we want to be able to find them. Okay, like, so this question, you'll have some of these in your homework, and it's going to say how many solutions are there, and what type of answers. In other words, what kind of roots are there? So b squared minus 4ac would be 10 squared minus 4 times 1 times 23. That would be 100 minus 92, or 8. That means there's 2 real roots. The graph crosses twice. This is a horseshoe up. The graph will cross twice. That's all you know from that. If you have to, you have to. Okay, but again, it's just not that big a deal. Just do b squared minus 4ac and have the chart. It's right in your book. You can just flip the page to the chart and you can say there's 2 real roots. If it's a 0, you say there's 1 real, rational root. And if there's a negative, there's no real roots. Okay? This is just part of the quadratic formula. So I'm not going to sit here and go through that kind of thing. We just don't care. Find the discriminant. We don't care. These application problems are huge. Again, they're so important and they're so critical that we are going to stop instruction for a little bit tomorrow, I think, or the next day. Anyway, we're going to do a couple of days where you're going to have some application problems. The first type of application problems with quadratics typically is a dropped object. So we're looking at, literally a dropped object, bam, okay? And everything on Earth or on whatever body of you're on is going to behave the same way. So when you drop an object, it's gravity pulling it to the ground. Doesn't matter what the object is, they're all going to fall at the same speed. Okay, they're going to increase at a relative speed to gravity, whether you're in feet per second or meters per second. This is dealing with feet per second. This is the dropped object problem. Now, one of the things that you have to get in your head is that this is the height of the object after t seconds of letting the object go. Height compared to time. It's time controls the height. Time is t in time in seconds. H sub 0 is your initial height, and h of t is the height of the object after t seconds. The height of the object after t seconds. So you can figure out the height of any object based on how long after you let it go and how high you dropped it from. The path of the ball is not what this equation is identifying for you. When you drop an object, the path is straight down. You let it go, straight down. Okay? What we are looking at here is not the path of the object, but the height of the object plotted over time. So when you let it go, you let the ball go, it's at its maximum height, the drop height, h sub 0. As soon as you let it go, it starts going towards the ground, but it's going slow right after you let it go. And then it starts going faster and faster and faster and getting closer to the ground until, bam, hits the ground. This is the graph of that height over time. It is a parabola. And it is half of a parabola where this is being the highest point. Does everyone follow that? Okay. This picture is not the path of the object. This picture is the height of the object graphed over time. And sometimes I don't do a good job explaining that. At my mom's house, a lot of times we would go to my mom's house right now, Google Earth. My mom lives in Massachusetts on the Cape. And they have a house that is literally, if you've ever seen the state of Massachusetts on a map that has that arm that comes off, my parents live right at if you follow the coast, the arm that comes out, they're right here on the bay side, the Boston side of the Cape. There's a canal that prisoners dug years and years ago in the early 1900s. They dug a canal. It's huge. It's like 7 or more miles long. And it's pretty far across, and big ships can get through it. It's deep. They live on the mouth of that canal. On the East Coast, now I'm not saying that they have it on the West Coast, but on the East Coast, everywhere I went as a kid, the beaches had these rock protrusions that were man-made coming off the beach. And you could, what we call them jetties. The rocks would just, like if this is the shore, the rocks would come out, and they were, in some cases, massive. And they were to prevent erosion of beaches. Well, in Massachusetts, at least on the Cape, you can go clamming. There's clams that live in the sand. And when it's low tide, you go out and you find the clams and you cook them and eat them. The seagulls like the clams too. And outside at my mom's, you can watch the seagulls when it's low tide. They'll come around, they'll walk around, they'll dig a little, and they'll grab a clam. And they'll take the clam up, fly it over the jetty, and drop it. That's what we're looking at, the dropped clam. Okay? Very different than if the seagull flew up and went, whoo, and threw it sideways. They don't do that. They just bombs away. Yeah, they land the shell on the jetty, It breaks, then they fly down, and hopefully they get there before the crabs, because the crabs will fight them for it. Okay, so they can't go too high, because then the crabs win, and if they don't go high enough, the poor clam goes kink, 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 and then it has to go back up again with the scrambled head. So this is height, not path of the object. We're going to talk about path of the object in a minute. You got to keep this, because we're going to give you another formula in a minute. We're going to keep this one for dropped objects. So if you could stand atop the Empire State Building and drop off a bowling ball or anything else, doesn't matter what the object is. So you drop it off, and we say from a height of 1,454 feet. Now, if this is where the 1,454 is, clearly that would be impossible to do, because if you dropped it from here, it would land on the roof. But let's just assume from the lookout you could reach out and drop the bowling ball and it would go to the ground. 1,454 feet. How long till the bowling ball is halfway to the ground? Okay? How long till the bowling ball is halfway to the ground? Remember, your function is h of t equals negative 16t squared plus h sub 0. The only thing we're adding to the equation is the 1454. That's where your object is starting from. I grew up in Massachusetts. The Empire State Building, not that far from us. I've been there. I'm not a big fan of big, tall buildings, but I've been there. There was a lot of rumors going around, like, if you dropped a penny off the Empire State Building. Did you have those rumors when you were kids? Like, if you held your hand out, it'd go right through your hand. If it hit the concrete, it would be like a foot deep in the concrete. Okay? That's all bull. It's a penny. It's so light that the air is going to cause a problem with that. We have no air in math world. So none of that is going to apply here. All right? The penny's not, we have air. So it's not going to happen. Yeah. The weight has nothing to do with it. The weight has nothing to do with it. So in math world, theoretically, if you took a feather and the bowling ball and dropped them both, no air, right? They're both going to fall and hit the ground at the same time. Okay? Now with air, then we have that problem where maybe weight and form does play a little bit. You have this thing with terminal velocity and all of that. But that's why I think we're using a bowling ball, so we can pretty much negate the air resistance. Yes, sir. Well, we're not doing anything yet. We're going to answer, there's two questions. The first one is how long until the ball is halfway to the ground? What do you know about the ball when it's halfway to the ground? There's only two things you can know. Time and height of the ball. Do you know either of those? Okay, how high is the ball off the ground when... Where should I put that? Where should I put that? H of t. 7, 2, 7. How are we going to solve this? How are you going to solve this? So you're going to get negative 727 equals negative 16t squared.
Divide both sides by h1.
Nope. Yeah, let's just get the whole thing. We get 727 over 16 equals t squared. And then square root. So you get the square root of 727 over 4 is equal to t, and that's plus or minus. Now, is 727 a perfect square? Can't imagine. So this is an application problem. Please don't tell me on an application problem, Mr. Lockery, it's going to take the square root of 727 over 4 seconds to get to halfway to the ground. What should you tell me? Yes. To the nearest thousand. So, and it's not negative, it's only positive. So the square root of 727, whatever that is, 20 something, and divided by 4, how much? 3 decimal places. 740. Everybody concur? 6.740. So that means it's going to take 6.740 seconds to get halfway. Now you should know the next question is a trick, right? The second question is, then how long will it take to hit the ground?
6.741.
Uh-oh. Dude, you're killing me. 6.741 seconds to get to the ground. So, now we want to get it to the ground. You're halfway, so how long does it take to get to the ground? No. Remember, we let it go. It took 6.7 to get halfway to the ground. We're still going. Yeah, so anyone who's thinking it's double that, not. You're falling into the trap because you are accelerating as you go. So every second you're going faster. So how do we find out how long it takes this ball to hit the ground? If I knew the time, I wouldn't have to do any work, right? Set the height to 0. So we want to come down and we want 0 to equal negative 16t squared plus 1454. And then we're solving again. Okay? So negative 1454 equals negative 16t squared. And you're going to get 1454 divided by 16. And then we square root again. Plus or minus the square root of 1454 over 4 is equal to t. How many decimal places? 3. But don't round until you get to your final answer. You're going to do the square root of 1454, divide by 4, then round. Do not round in the middle of your problem. If you have a multifunction calculator, you can do it in one shot, as long as you close the parentheses on the radical. So this is going to be less than 13 seconds. How much less? What's t going to equal? 9.33. Everybody agree with that? To the thousandths? No? So the time to hit the ground, 9.533 seconds to hit the ground. Anybody have a question on that? What do you know? You either know time or height. Those are the only two things you can know. Your question is, which one do you know? A dropped object has no vertical velocity. Okay? A dropped object has no vertical velocity. So if I let it go, it's starting off with a vertical velocity of 0. If we throw it, even if we throw it down, straight down, then we're increasing vertical velocity. That's going to change everything. If those seagulls could throw the clams, that would be a whole different deal. So you watch a little kid. Little kid comes along, finds the clam. sees the jetty. Little kid picks up the clam, and the little kid throws the clam. Doesn't hit the roof because there's no roof outside. Okay? The path of the clam, the path of the ball, the path of anything launched that doesn't have a power source. If you look at the path, what shape is the path? Even if I throw it like that, the path of the beam thing is parabolic. Even if I have a gun and I take the gun and take aim and shoot, the path of the bullet is parabolic because the bullet does not have a power source on board. It is a launched object, albeit a very fast launched object. Okay? Yes.
What about light?
What about it?
Isn't it being launched?
The particles are, now you're in physics,
And you're talking on the
and you're,
scale.
we got a few things. The particle of light, just the particle itself, theoretically would be parabolic. However, light travels in a wave, and so that's where we leave my element. So if you want to treat light as a particle, you need a physicist, of which you might want to check out the Big Bang Theory. They could probably help you. That's not my deal. Mr. Miller could help you a little bit. Try to think more in terms of something that you personally can launch. Yeah, you kick a soccer ball. You hit a golf ball with your golf club. That's a launched object. You take out the gun and you shoot. My favorite example this summer, we may have talked about it, was the archery. Did anyone see any of that this summer? Did we talk about it? It was unbelievable. Because they would stand behind and you would watch the guy and he'd go like this, and then boom, and it goes into the bullseye. Wow, big deal. Then they put the camera over there, and you watch them do it, and you go, holy crap, those arrows were doing this. And then boom, right into the bullseye. Now that really was impressive to me. Because there were so many variables they have to account for that it becomes a big deal. We'll come back to this in a second. This is what we should be teaching you right here. Okay, this is the formula that we should be teaching you. This is the formula we're going to teach. And you can see right here, this is the difference. We are only going to tell you about the part that is the gravity, the vertical velocity part. How many of you saw Lethal Weapon? Danny Glover and Mel Gibson. There was like 4 of them. The first one was really good. The rest of them just like most not so good. In that movie, Mel Gibson, the crazy one, comes over to Danny Glover's house. They have dinner. His wife is a crappy cook. They're taking the garbage out, and Mel Gibson's going home. He gets to his truck, and they're talking, and he says, you know, I'm really good at it, or I do it really good. And he says, what's that? And he says, I kill people. I'm good at it. One time in Laos, I did a guy from 1,000 yards out. Now, 1,000 yards is about 0.6 of a mile, if I'm not mistaken. We're talking about 3,000 plus feet. Okay? That's a little bit more than half a mile. That means in order for him to look at the guy and shoot the guy from a half a mile, he's got to aim the barrel of the gun significantly higher than right at the guy. That's a pretty big deal. Gravity is going to pull it down. If you've seen the movie Shooter, more modern movie, Mark Wahlberg is in there, and they talk about shooting the president, and somebody shoots a guy standing next to the president. He talks about what those marksmen do in the Army, in the Air Force, all these special forces guys. He talks about the trig that they have to do on the fly, and in some cases in their head. And back then, they didn't have computers to do it. They had little booklets that had all the information in there that they needed. They had to figure out wind velocity, humidity, all of these variables that we're eliminating for you. We really should be talking about this in more detail. I want you to understand that. What is it that determines the path of the bullet? It's the angle of the gun, the velocity of the bullet initially, and gravity. And let's not worry about wind, and let's not worry about humidity and those things. But I want you to understand the angle has a big deal. It's a big, important part of this. Natalie Gulbis, she used to sit in this room. She's a golfer. And I golf, but she's a golfer. And at 16, she could tell me so much about the physics behind the golf. Every club has a different, every iron has a different angle, the club face. Some of you are probably golfers. You know more than I do. We used to do these problems when she was in this class. And we would talk about, well, if we take out this club, what's the angle that the ball will be launched at? That's going to go right here. And then we can talk about her club head speed as it comes through. If she takes a full stroke, she could tell you how fast her club head was going. And then she could tell you how far the ball was going to go. And that's how good she was at it at 16. We're eliminating this, and we're going just to this. So when you hear initial velocity for us, it's vertical component of the velocity. It's not how fast the bullet is moving. It's how fast the bullet is moving vertically. Does that make sense to everyone? This is, for me, this is a little bit of a tricky concept, and I don't want you to leave thinking that when we tell you initial vertical velocity, we're not talking about how fast it comes out of the bullet, how fast it comes out of your hand. We're talking about how fast it's going up, in essence. Just the up. Is that clear to everybody? Okay? Go ahead.
Bring it down with the...
Then you would have a negative vertical velocity. So you would be still increasing how fast gravity is going to pull it to the ground, right? And there's a problem in your book where they talk about a volleyball player going up and hitting the ball down. It's a dumb problem. And that's it's a dumb problem. Why is it a dumb problem? Because the question is going to be, how long does it take to hit the ground? So the volleyball player goes up and goes, hip-hip. How long does it take to hit the ground? Yeah, teeny weeny. And that's just hard to work with. So we try to avoid that, all right? And we're trying to get you to think realistically. Please think realistically. If somebody picks up a ball and throws it, and it's the strongest thrower that you could ever find on this earth, they can't throw the ball, and your answer be that it took an hour for the ball to hit the ground. It took 38 or 384 seconds for the ball to hit the ground. You can't do that. What was the maximum height of the football? 251,398 feet. Okay? Not going to happen. You're talking about miles now. Somebody took the ball and threw it 5 miles in the air. Really? Okay? Can't happen. If that happens to you, it means you make a mistake. Go back and fix it. Here are the components. Vertical velocity only. Still starting height. Still gravitation, we're working in feet. If you see a negative 4.9, you must be working in meters per second. So everything will be changed to meters, and they'll tell you that. This is the height. This is the time. This is the initial speed, and this is where it starts from. If they're hitting a baseball, the starting height might be 3 feet. If you're throwing a football, the starting height might be 7 feet. If you go up to the top of a building and you throw something off the building, the height will be whatever your height is there. Remember, you also have to take into account the specifics. If the building is 40 feet tall and you're 6 feet tall and you're going to release the ball from eye level, what's the starting height of the ball? 46. These are the details that are going to separate you from the other people who struggle with this stuff. So when you look at this, You launch an Angry Bird, right? It's going to follow a parabolic path. It's starting from a height of 80 feet with an initial velocity of 64 feet per second. Again, this is the process that you're going to see. What does it look like? It looks like this. This is 80 feet. And the bird is going to go up and then down. Write the height model for the object. See if you can write the function based on the given information. That's the first question. You're looking at a test question right here. See if you can write the function. And again, we're not asking you to do anything tricky here other than what's the function? What's h of t? Great, what you get? Why not? Okay. Nick, what you get?
Negative 60 plus
64, that's the initial velocity.
plus 8.
What goes after the 64?
Oh,
T plus 80. That T is one that's really a common, I forgot it. Really a common, don't forget that second variable. This is a quadratic function. How many seconds until the maximum height is reached? Where does the maximum height occur? What's it called?
vertex.
Vertex. Here's the vertex. This variable, the one that's horizontal, is which variable? Time. In this, the vertical variable is your height based on time. We need to find t, comma, h. This is the vertex. How do you find the t coordinate of your vertex? Very good. So the t coordinate of our vertex is negative b over 2a. And we're going to get negative 64 over 2 times, bless you, negative 16. How much? 2. So that's going to give you positive 2. So after 2 seconds, you're at the max height. And make sure you answer these questions in words. These are word problems. Any questions on the t coordinate of the vertex? The follow-up is, what is the maximum height? T stands for the time for the vertex. The t coordinate of the vertex. Yeah. Remember, the vertex is 2 variables, time, comma, height. Every single point is time, comma, height. How do I find out what the maximum height is? Plug in your time of 2. So in here, h of 2 is negative 16 times 2 squared, 64 times 2, and 80. So h of 2 is 144, so max height is 144 feet before the Angry Bird starts hitting the ground. And then the fourth question, how long till it hits the ground? Plug in 0. Now, sometimes this will be factorable, and maybe this is one of those times, but I usually just go straight to quadratic formula. Now, you need to understand you have a quiz tomorrow. Check your calendar. This is your homework here. It's not homework 23. Look on your calendar. So I give you the calendar. And I think this is the same assignment as well. If it's not, check your calendar. Okay?
Personally, I don't think it's every sign of A of
When
one.
you're free.
I think that's the better.
On the first, oh, you were on the picture. We can do it first day. All right.
Hey, Mr. Lockray,
Yeah.
for that sign of P, the BO, would that be BO the vertical velocity?
V sub 0 for us is vertical velocity. For that other one, it's velocity of the object.
Okay.
Initial velocity.
Got it. Oh, so
It says on the calendar. It'll say right up there. The calendar's over there also.
Oh, I went to the quiz from Friday.
Okay. Who else? Amanda, Reese. Who else? Gracie.
Yeah, I think I left it at my house because,
Make sure you bring it to me tomorrow.
okay, is there any possibility that you could like just have the party instead of stamping it?
Those are extra credits, and if you're not here, that's how it works. Which one? First one.
No. Oh, Alfie. I think
Did we already have this conversation that I didn't have one for you?
there are two Allies in the
I would
class.
rather not have an Alex here. From Friday.
Might be under Allison.
No, I don't, I mean, I literally don't have one. This one's good to go the way it is. Make sure you make the list, make sure you use the Google.
Maybe you accidentally marked this here.
Could have.
It doesn't say it. Okay.
This is,
Oh, I wasn't.
so, here we are, right? There's
Yeah,
your
that
list.
was
4, 6, 4, 7. Yes, Locker Boy?
I'm going today.
Uh-huh.
That's my unit 1 test.
Can you see it?
Yeah, I want to see what things.
Third drawer down,
Oh, I think I
probably
missed.
locked. Check first. See if the third drawer is locked.
Okay. Yeah.
Made it.
Yep.
What are we doing?
Making a file.
Okay, let me see what we find. Maybe get his first. Pull open third drawer. First period or second?
Not first.
All the way to your right. Second folder from the right. Oh, you
Yeah.
want the test or the quiz?
Oh, the test.
The test first folder.
Yeah.
That's your chapter 1. One's a quiz, one's the test.
Okay.
Find yours. You'll find yours first. Wait a minute.
Looking for my bigger one. Or our quiz in here?
dig them out and look at them, but you can't take them out of here. Here's that. Let's see.
This is the same difficulties test, right?
I don't know, it's quiz difficult. I don't know what. The test is harder, for sure. Why don't you sit someplace different, please? What did we say, Luke? A or A?